So, hello everyone. Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. So today's session will be a bit interactive. I want all of you to interact. So I get to know about the Kurshid. Kurshid is a BTech pass out. So can I know about all of you? Kirti, can you introduce yourself?
Yes, ma'am.
Yeah,
Hello, ma'am. Good evening.
yeah. Good
Um,
evening.
myself, Dr. Kirti Thakur. I'm working as an assistant professor in Government Engineering College, Avsari, which comes under Pune district.
Okay, nice, Kirti. So I should call you Kirti, ma'am. So you have
No,
done
no,
PhD
it's
from
okay.
where?
COEP Pune,
Okay, nice. So you are teaching in government, which college? I didn't heard it.
Government College of Engineering and Research, Avsari.
Oh,
It's the
sorry.
only government college in Pune district, ma'am.
Okay. Nice to know that you are here. And Akhila?
Yes, ma'am. I am Akhila. I am pursuing BTech third year, ma'am, from Sri Padmavati Mahila University.
Okay, nice. And
Thanks.
nice to know. Yeah. Tell me. Akhila, you were saying something?
Yes. No.
Okay,
Yes, I am saying thank you, ma'am.
okay. And Meenakshi? Hi, Meenakshi. Hi, Meenakshi. Hello. So, okay, I think Meenakshi is not responding. We will wait for 2 minutes more because I think NS Murthy Sharma sir and other will join most probably. And regarding week 5, you will have the assignment for week 5. But I must say that we are instructed to solve your doubts and your problems in solving the questions. But we are given like week 1, week 2, week 3, week 4 and then week 5. So we have to go like this only. So I can't jump to week 5. You can ask other TA. Are you guys attending other TA, Miss Singh, Mr. Singh? Mr. Singh live session?
One time I have attended, madam.
Okay, one time. What
Yes,
about you,
ma'am.
Kurshid?
I have missed one live session, ma'am, which is regarding to week 1 and 2.
Okay. Okay. He most probably deal with the questions mainly. But we have to go like this only. And so all of you have introduced yourselves. So I'll like to introduce myself. So I'm currently pursuing direct PhD like after BTech in IIT Hyderabad, and I have been awarded with PMRF fellowship. So as a part of PMRF, I am taking these live sessions. So I have done my BTech in 2020 from a Central University of Chhattisgarh. Then after that, I joined PhD here in IIT Hyderabad, and then I'm currently third year PhD student here. So I should say, but all of you who's like Kirti Thakur ma'am is already having PhD, but those who want to join PhD, they can also join PhD after BTech. So it's not like that you can have to do MTech first, then PhD. So Kurshid, if you want to join, you can join, and Akhila also you.
Yes, ma'am.
Yeah, it's
Yes.
very good opportunity. Like it can save years also. And if you have some research perspective, then you can join. It's good. And as Kirti Thakur ma'am is currently assistant professor, so you can get that type of job as well. So I think sir will not join, so we should proceed like this only. Uh, a question, I have given you one question for Fourier transform, like mod of x. Did you solve?
Yes, ma'am. Yes, ma'am, I did try. Actually, I was little bit confused what is x here. So I took it simply as function is mod of t and I solved for that
Yeah, yeah,
Fourier
yeah.
transform.
Yeah, mod of
Okay,
t.
ma'am.
Yes. So,
Yes, ma'am, I did try.
yeah, how to solve
Yes,
it?
just one second, ma'am. Let me check it. Ma'am, I simply took like t ut minus t u of minus t for t less than 0.
So you are solving by just formula, right?
Yes, ma'am, just formula. It came out to be minus 2 by omega square Fourier transform mod t.
Minus 2
Minus 2
by
by.
omega square. Right, right, right. So answer is this one only. So these type of questions actually make you aware of the Fourier transform and all. So so you should be able to solve. Then if the question asks what is the Fourier transform of 1 by t square, then what is the answer? So you
Yes,
have to
ma'am, 1 by t square. Okay, it will be minus of this and ma'am, it
it is
will be 1 by
something
minus
similar to mod of omega, right?
mod of. Yes,
Because
ma'am.
you were having the duality property. Hmm. So just keep in mind, for example, in your exams, people generally ask about these mod of t square. So you can't just use formula there. So you should remember these things. So I think, yeah, we should proceed further. Once a second, I have to check whether recording has started or not. So yeah, recording has been started, and we'll move ahead. And one more thing, if you want to meet to have a particular session on particular topic, just so sorry, the meeting got cut, I think due to some network issue. So yeah, we'll try. So I was telling, so sorry, meeting was actually off due to some network issues going on in IIT Hyderabad. So I was telling you that if you have any doubt related to some particular topic, so I will deal first with the explanation, then with the related questions. Like I have some gate questions also, so you can we can have some interactive questions also on that topic as well. So right now I'm dealing with whatever the sir has taught you in the class. So moving to ahead, introduction to quadrature carrier modulation and demodulation of QCM. So I hope all of you have had already watched these lectures. So basically you should get minimum of 25%. 25% is weightage is given to assignments, and 75% weightage is given to exam. So before exam, I will arrange one proper session on your probable questions, so that you won't have any problem in exam. So but I must say, just to follow this assignment questions, you will have the similar questions in the exam. I have already given this type of exam. So in Aditya sir course, you don't require much deeper knowledge, but yeah, you should know where the term has been coming. But yeah, you can definitely pass this exam, and 25% is given to assignments. I think it is quite easy, so you are able to do all those two questions. So yeah, please make sure this thing. Okay. So quadrature carrier multiplexing. Till now we have discussed AM modulation, and in that DSB, SC, and SSB. So we know that AM modulation have this type of spectrum. So if we only require this one without carrier, so it is DSB, double sideband, this one. So yeah, so the color in red is a DSB, and the color, we'll take different color. The color in pink is SSB. But yeah, make sure that we are not using the impulse, because impulse is waste, because it is a carrier signal, and carrier signal just carries information, it has nothing in it. So okay, so this is what. So now the term comes as a quadrature carrier modulation and demodulation of QCM. So whenever you use a two terms, which is perpendicular terms, which is cos and sine, so we use quadrature. Quadrature means it is a quadrature in magnitude, the quadrature in nature, and sine and cos you all know. So here we will see the basic structure of this. So since quadrant, if you will, if a 90-degree phase shift will have a sine to cos conversion. So this one should know is all school to college. So here in the first quadrant, positive, positive, negative, negative. So here in the first quadrant, you have all trigonometric function as positive. And in second quadrant, you only have sine, and what is the opposite of sine? Like 1 by sine?
And cosine.
No, cosine is not. Yeah, cosine. So cosine. And here tan and cot. And here cosine is not, name is not there. Some cosec. Uh, cosec. Yeah, cosec.
Yes, ma'am. Cosec, cosec.
Yeah, yeah. Cosec. And here cos and opposite of cos. What is the opposite of cos?
Sec.
Sec. Yeah. So sec here, it this these terms are positive. So you just remember this all school to college, which is the this symbol you can remember, so that whenever some question comes, then you can just follow this. So here you should know the phase difference between these two carriers is pi by 2. Hence the two carriers are said to be in quadrature. Now we observe that the phase difference between two carriers is 90 degree, and the phase difference between two carriers is a pi by 2 radian. Radian is equals to 90 degree. And just a simple formulation. What is the conversion formula from radian to degree? So 180 degree by pi into radian is equals to degree. This is the formula. So whatever radian you have, you just multiply this, because radian will be must in pi terms. So it will be just cancel out, and you will have this formula. So moving ahead, if we consider the modulated signal given as ACMI T cos 2 pi FCT minus ACMQ sin 2 pi FCT, here two message signals MIT and MQT. Here I and QT, different signals we are just considering. Just to remember this thing, like in modulation, whenever we multiply any message signal with a carrier, then it will be a modulated signal. So we are multiplying one modulation signal with one carrier. Here it is one carrier, and here it is second carrier. And carrier can be cos or sine. So I will ask one question: why we are taking carrier as only cos or sine? Why we don't take this signal? Why we don't take this thing signal? These are also signals, right? Cos signal is this one, sine is this one. Why we are not taking this thing? So the answer is every signal can be represented as some harmonics of sine and cosine. So at the end we only have sine or cosine, so we take sine and cosine. So these are the reasons why we take only sine and cosine. And also, in one of the question was asked in my interview was this, like why we take only sine or cosine. So also we saw using Fourier series, like we are representing a periodic signal in terms of the harmonics of sine and cosine. So this is the reason. So moving ahead, here we are taking two message signal, MIT and MQT. So in this term, MIT is a message modulated on cos 2 pi FCT, which is in phase component, and M QT is the modulation applied on quadrature on out phase. We call it out phase also, quadrature carrier. So in phase and out phase. So suppose we have this one x and y, and you have suppose a vector v vector. So you know that this is suppose an angle it is making with the x direction. So you know what is this term and what is this term?
Yes,
What
ma'am.
is this
Along
term?
x-axis cos theta term, v cos theta, and there will be sin theta.
Yeah, very good. So here he is a magnitude. So similar way, we are just and this angle is 90 degree. So similar way, we are just modulating in the one in phase and one is out phase. And there is what is the importance of why we are doing this. So here the importance comes why we are doing it. Two messages multiplexed on the quadrature carriers, and this scheme is called a quadrature carrier multiplexing. So where it is used, so when we try to analyze a signal, when we try to analyze a signal in with respect to a quadrature as well as in phase, how it is behaving with the 90-degree phase shift, so we require this QCM. And it's simply when we see a force diagram as well, so we require to have these two components, in phase and out phase. So it's in the same way we are trying to analyze it for the modulation case. So now what is that? So we have two messages which are multiplex on the quadrature carriers. Hence this term is called a quadrature multiplexing, carrier multiplexing. And you know that sine 2 pi FCT multiply cos 2 pi FCT. What is that? It is a 1 by 2 sine 4 pi FCT, because sine 2a is equals to 2 cos a into sine a. So similar formula we are applying. So we will have when we can pass the signal. When we can pass the signal, when we'll have the band pass signal as 2fc, right? Because here the center frequency is 2fc and 1 by 2. So we can pass the signal. But when you will have the low pass filter, so low pass filter won't be able to pass this, because here you will have sign as this one and this one, 2fc minus 2fc, 1 by 2, 1 by 4, sorry, already 1 by 2 term is there, f sine 4 pi fc. So you have to properly choose what is the center frequency for low pass filter and the high pass filter. So I was multiplying this because for the demodulation case, you just multiply the two signals and try to recover it. So if we multiply or demodulate this, that is we are multiplying at receiver by sine 2 pi FCT, demodulating cos 2 pi FCT by sine 2 pi FCT gives this one. We all know. So if we pass low pass filter, it will result output as 0. And what we require, why we want it to not pass, because it is a carrier signal, and at demodulation we don't require carrier, we just require message signal. So this is not passing, so we just want these two carriers to remove at demodulation. So the two carriers, 2 cos 2 pi fct and sin 2 pi fct, are orthogonal because we do modulate with the cosine or sine, it will result output as a 0. So output is 0. Now just we will see the demodulation with cos to pi f ct. We know that with while modulation we are multiplying with the carrier signal, and while at the demodulation also we are multiplying with the carrier signal. So we can either multiply with the cos to pi f ct or sin to pi f ct, because these two are the carrier signals. So xt multiply with cos to pi f ct will give this one. Xt is a modulated signal, and we know that modulated signal is ACMIT cos 2 pi fct minus ACMQT cos 2 pi fct. So here, and one more thing, while for the demodulation, we only use low pass filter, while for the modulation, we only use band pass filter. So yes, and when you will have this one, so you will multiply and get this one. So when you pass with through a low pass filter, you will get only this term, ACMIT divided by 2. So what I'm going to say, when you modulate, when you demodulated with cos 2 pi fct, you are getting in phase component with some scalar AC by 2. But when you demodulate sin 2 pi fct, you are getting AC by 2 MQT. So in phase component itself gives when you modulate it, demodulate it with cos to pi city, and out phase component also gives with the when you demodulate with the sin to pi city. So this is a basic thing, and you should remember this. So moving ahead, this is not anything, and just telling how you can. So I think all of you have watched this lecture. So can somebody tell me what is the low pass filter frequency? What should be the low pass filter frequency?
Ma'am, it should be less than two times carrier frequency, but it should be greater than message frequency.
Yes, yes, yeah. So we want message signal to go out, go out of the this signal, but at the same time we want the carrier signal to
Yes,
go.
ma'am.
So it's
And this is ma'am,
equal
at
to,
baseband only. This message signal is at baseband only, so that will be simply greater than message.
and definitely this one is 2FC is far far greater than FM. So moving ahead, demodulation process is taught in this class. So I think I should not need with this. Sharing with same bandwidth. I have come with the questions. Wait, I'll also this one. SSB-SC signal. This is also taught in the module 4. So yeah. So we know that how the DSB-SC signal looks like, and then how the sideband modulation looks like. So we know that the DSB-SC is simply this one. Now, if we want only sideband, then we have to pass it through a low pass filter. Sorry, a band pass filter. So yeah, filter. Yeah. So do you guys know about this sampling theorem? Why I'm talking about the sampling theorem? Because a sampling theorem is a theorem which deals with which tell you a minimum a sampling frequency, so that you can easily recover the message signals whatever you are doing. Because what is happening in the communication system, you have
Ma'am, it is
multiple.
two times the largest frequency component in the signal.
Yes, yes, it is a Nyquist sampling theorem, right? So how it is
Nice.
coming two times of FM again in frequency component?
Ma'am, that I don't remember.
Yes. So, and the question, this is very important and it is a basics of signals and system. That is fine that you are not remembering because it's some definitions and derivations are required for that. But yeah, why I'm teaching here, because you should after all in modulation you are just referring with the filters, and then after filtering only you will getting a message signal as well as a modulated signal. So at the same time you should remember in your mind like whether it is affecting a sampling theorem or not, because a sampling theorem is that which is required to convert a signal to a digital signal. And all we have, for example, I'm speaking, this voice signal is an analog in nature, but for the actual communication system to work, we require to pass it through a sampling theorem so that we can convert to a digital, and we can further modulate it, and we can use it for our purpose like QAM, QPSK, BPSK, these things. So sampling theorem is required for encoding, decoding, everything. So I'll just briefly describe it here in this page. Uh, Sampling theorem is useful for filters. What is the samples required? So whenever you have a signal which is analog in nature and you pass it to a sample circuit, what is sampling and holding circuit? So you are taking a samples means you are just a switch. It is just open, off, on, off, on and off. So similar to this, you will have these many samples. So what is the sampling rate so that you are able to recover this particular signal at the input? So what should be the fs so that you can easily recover the input message signal? So from Nyquist criteria, we have found that qs is equals to fs is equals to 2fm, and this is a simple sampling Nyquist rate. But Kushit, I would like to see also a band pass sampling. This is the homework for you. Band pass sampling, it is very good thing. Band pass sampling, here it is not necessary to have fs is equals to 2fm. So please look at this. Now why this comes, I'll just uh, try to write it. So what is sampling?
Ma'am, is it related to, excuse me, ma'am.
Yeah, yeah.
Is it related to that impulse train sampling property of impulse?
Yes, 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 yes.
This.
Sampling theorem is all
Okay.
about that. But yeah, band pass sampling means you are not passing it through a low pass filter. Here you are passing it through a
Yes.
band pass filter. So here you are passing it through a low pass filter. But here you are passing it through a band pass filter. And here it is not necessarily equals to fs equals to 2fm. So here it is not necessarily. But nobody talks about it. But in gate questions, we directly have these questions. Uh, so I want you all of you to look at it so that you can't miss this type of important questions. So yeah, sampling theorem. What is sampling? So sampling is just a multiplication of xt into a impulse train. It is xst. So it is in time domain and it is a multiplication of this one. So in the frequency domain, how it will look like? xsf xf convolution of xsf, right? Now, the impulse train is a periodic function. We all know that. Xs, xst. So yeah, sampling theorem has a three types. First in impulse sampling, at page. So you have three types. First one is impulse sampling. Second is pulse sampling. Third is flat top sampling. I want you to remember the derivation as well. It is not remembering. It's just a trick you can remember. So if you know this, you can face many interviews. So yeah, impulse sampling here in we are multiplying a signal xt by a impulse train, and here we are multiplying a signal xt by a pulse train, and here we are multiplying a signal xt by a pulse train with flat top nature, flat at amplitude we can say. Yeah, so impulse sampling will look like, suppose this is xt and you are multiplying with the impulse train t, it is ist mt, I'll say xt. Here you will have this one, this one, this one, this one, xst. So I will derive it for impulse sampling, and you guys will have the homework for pulse sampling and flat top sampling homework. It's very similar and easy. You can do it. So here the impulse sampling xst. So I'll change the color. So what is xst? xst is x. I just want that after this derivation you don't forget anything about it. So it's a multiplication. Here the multiplication sign ist. So when you Fourier transform it, why we do Fourier transform only? Because in Fourier transform we can only calculate the bandwidth, and bandwidth is very rare, like a rare species. So all of the world are going to save the bandwidth and the methods to save the bandwidth. So we are just trying to see it in frequency domain. And just whenever you have a doubt like why we are doing, just ask yourself why it is this, why it is this, why question should come in your mind every time. So it is a convolution. It's just not like circular convolution, because it is a time continuous time. In discrete time, in periodic time, we will use circular convolution. So I just want to ask one thing. Here I'm using small x. Here we are using small x and capital X. So Fourier transform, it's just not a function difference. Like suppose it is in time domain and frequency domain, we are using this. No, this is wrong. Here in time domain and in frequency domain, capital X. Because these two are a different function. These are not the same function. In same function, we can do this. So it is not a same function. It's just a complete different function. So you should remember this. So battery saver is on, I think. Okay, so I have charged my laptop. It's charging, yeah. So, okay, we know that this XST, so one should tell me this one should be I, cap small I. Everywhere I'm using small I. So, IST is a periodic function, periodic signal, right? Because we know that it's an impulse train in time domain, IST. And it is repeating its behavior after a particular time period. So we can write IST in the form of, tell me.
Ma'am, it will be of similar nature with the magnitude 1 by t.
Fourier series. Yeah, yeah. Yes, very true. Fourier series, because here it is a periodic signal, so you can write in terms of Fourier series. And what is Fourier series? Fourier series of a time domain itself. It's not a frequency domain. Fourier series a time domain representation of the periodic signal in the harmonic of sine and cosine. So I'm trying to write harmonic of sine and cosine. So you can write IST is equals to summation of Vk e power j 2 pi k f naught t, k tends to infinity to infinity, and Ck is equals to 1 by t integration over t, here t, um, RT e power minus j 2 pi k f naught t dt. So whenever the integration term comes, here you will have the negative sign, and whenever you have normal terms, you will have the positive sign. Just remember this. And now solve for Ck. Yeah, now solve for Ck. 0 to t. We know that here IST will only have the term as 0, right? Because we are representing not IST, it's an impulse free. So here it will be 0, 1 dt, because IT only have the magnitude at this one, right? Delta t. So it is a delta t. So whenever you have doubt in some representation, just try to use whatever you have read till now. So t is equals to 0. You know that delta t is equals to 1 at t is equals to 0 and infinity 0 otherwise. 0 otherwise. Why I'm taking 1? Because for the discrete signal we are taking. So you can say as a discrete signal. No, no, no. No, continuous itself. So you will have this one. Del t is equals to 0. J to pi k f naught into 0 dt 1 by t 0 to t 1 into dt. So 1. Is there anyone having doubt? I'm trying to write the impulse signal in the form of Fourier series. How will you write?
Ma'am, I think it should be 1 by t because it will be integration of impulse and that area is unity.
Yes, yes, yes. So I have done wrong.
And so it
It's an
will be by-
impulse, right? That's why I was
Yes,
taking
ma'am,
there as
1 by
positive.
t.
Huh. So it should be 1. Yes, yes. Very nice. So you remember these things. It's very good that you are remembering. Ck is equals to 1 by t. Okay. Then how will you write this? Is is equals to Ist is equals to 1, k is equals to minus infinity to infinity, 1 by t e power j 2 pi k f naught t. So it will be definitely k is equals to minus infinity to infinity, 1 by t e power j 2 pi k f naught t, right? So it is Ist. Now moving to the equation number 1, xst is equals to, what was that? Xt multiplication of ist. So I'm just writing xt is equals to multiplication of 1 by t, k is equals to minus infinity to infinity, e power j 2 pi k f naught t. And just we are just taking in the Fourier transform, we take different color, xf into convolution of 1 by t, k is equals to minus infinity to infinity, e power j 2 pi k f naught t. Wait a second, I just check whether recording is on or not. Yeah, it's on. So, huh. So, yeah. question, how will we do them?
Ma'am, it will be for a periodic function. The Fourier transform is simply the Fourier series coefficient separated by the impulse. So it will be simply another impulse train of height 1 by t.
Yeah, yeah. So here I was converting everything in the Fourier transform. So how will you convert this one to a Fourier transform? You know that this one is a shifted impulse. K varies, right? So it will be a shifted impulse xf convolution of what was it? It's the integration of x 1 by t only. Sorry, it will be del f minus kf naught, right? Minus infinity to infinity, right? And you know that when we
Yes.
convolve with a del, shifted del, so you will have summation of 1 by t x f minus k f naught, k is equals to minus infinity to infinity. Very good question. You can succeed here. So yeah, you will have this one. If we plot this, Kirti, you are here now. I want Kirti, are you understanding?
Ma'am, not completely actually.
Okay, okay, I'll go through again then. I just want everything. So here in what is sampling? Sampling is just nothing a multiplication of a signal to a impulse strain. So we have three types of sampling. In impulse sampling, we multiply a signal with the impulse strain. In pulse sampling, we multiply a signal with the pulse strain. Why pulse? Pulse strain itself is a periodic signal. So we multiply it with a periodic signal so that you can have infinite samples, and the sampling rate, which is fs, is try to find out like what should be the sampling rates so that it will be easily we can recover the actual message signal which is sent at the transmitter. So I'm dealing with a impulse sampling, so I'm multiplying with a signal with the impulse string. This is a signal which is an impulse string, so that we can get a sampled version of signal which is xst. And now I'm trying to find the Fourier transform of xst, so that we can have a proper frequency domain representation, because at the end you all want a frequency domain representation of a signal so that you are able to calculate the bandwidth and analyze it for the using the spectrum analyzer. So at the end we want all the signals to be in frequency domain. So yes, so me and Kushal was trying to find this periodic signal in the form of Fourier series. So xst is written in the form of Fourier series. You know that the Fourier series formula is this one, which is equation number 1. And then we try to calculate ck, and we got ck as 1 by t. Here do you have any problem up to this?
No, ma'am.
So ck we got 1 by t, and then I try to write the ists in the form of this 1 by t e power j 2 pi k f naught t, and ist is equals to equation number 2. This one is ist is equal to 1 by t in summation of k is equals to minus infinity to infinity e power j 2 pi k f naught t. Now we know that this is from equation 1. xst is equals to multiplication of these two, and similarly writing in the Fourier series, using Fourier series, and we are trying to calculate using the Fourier transform. And you know that in multiplication we turn to convolution in Fourier in frequency domain. So Fourier transform, what is the Fourier transform of this one? It will be a shifted impulse, right, in the frequency domain, because in the time domain you have multiply with the e power j 2 pi k f naught t. So in the frequency domain you will have summation of delta f minus k f naught. So we know that the formula of this one, del t minus t naught convolution of x t, it is equals to x t minus t naught, right? We know that this one. So similarly we have applied for the similar way, like xf, here xf is there, then x f minus f naught with amplitude of 1 by t. I think you have got. So
Yes, ma'am.
yeah, so
Ma'am,
yeah,
I
yeah.
have, ma'am, actually, I was in thought of like I will get answer like why the two times FM is
No,
there
no,
in the
no,
sampling theorem.
just after that I'm telling you why we get. Just after that I'm telling you. So let us consider, yeah, this answer should be in your mind. You should never remember anything. You should know how it is coming. So you know that xf Suppose this is a baseband signal, F, baseband signal, W and minus W, we do usually represent, okay? This is the input signal. And what we are getting, XF is equals to 1 by T summation of K is equals to minus infinity to infinity X F minus K F naught. F naught is the fundamental frequency. Okay. So yeah. So just we are trying to plot this XSF. It will be this one. It will be this one. It will be, yeah, it will be XST. Fs. So F naught I'm telling is Fs, the frequency, sampling frequency. You can also say F naught, but you have heard about Fs. So only I'm representing F naught as Fs. Now this term is, if k is equals to 1, so here Fs. If k is equals to 0, this signal. If k is equals to 2, 2Fs. If k is equals to minus 2Fs, and this will goes on, and the amplitude will be 1 by T. So what here the W term is there, it is minus W. To here should be Fs plus W, and here should be Fs minus W. So you want Fs minus W should be greater than or equals to W, because you want this not to collide, because we don't want any information loss. So Fs is greater than equals to 2W. Hope you got this point. So this is the Nyquist rate, and we got using this derivation. I think you have got.
Yes, ma'am.
Yeah, so here from here we get this. So similarly, you can also solve for a pulse sampling and other sampling, and this is required for a filtering process. So yeah, moving to the single sideband. So where it is used, the sampling theorem in this SSB modulation. So whenever we try to use a filter, because here also, see, here also sometimes we want only this particular frequency, this particular, so we will use a filter of this particular band, but at the same time we have to make sure this is not colliding with other information, so that we don't have the information loss at the receiver. If you have information loss at the receiver, then we will come across with many losses. We cannot hear your voice if I am saying something, so it will come with a noise, so you won't be able to solve it. I think you don't have to remember anything about the sampling theorem. If somebody asks, just remember we are just writing the impulse train in the form of Fourier series. Then we are convolving it because it is in the frequency domain, and in the convolution we are getting the shifted version of the baseband signal in the form of sampling theorem in the sampling frequency. And why we require, because Fs minus W is greater than or equals to 2W. So Fs should be greater than 2W. Okay. So single sideband modulation. Consider a message signal empty. I think you all have watched this lecture, and this lecture is was uploaded very early, and you are just now in a week 5. So I want what is the final expression for SSB. Then we will move to the questions also. Final expression for XSB and DSB and AM. You should able to differentiate between these two. Yeah, tell me. You all have watched the lecture, I think.
Yes, ma'am. 1 second.
Yes, yes. We will draw the spectra then.
Ma'am, it is actually message signal multiplied by cosine of this carrier frequency, and then it will be added with this Hilbert transform of this message signal.
Okay. And in the
M
Nyquist, you
has
have taken AM, SSB,
yes, ma'am.
and DSB. So it's my habit, I don't remember anything. So I usually derive. So I also want you people to derive. Sometimes we have to remember some things, but yeah, sometimes it is not required. Kirti, have you gone through this lecture?
Yes, ma'am.
So AM, everyone remembers DSB and SSB. Tell me the expression for DSB and SSB.
DSB is simply my message
What
signal multiplied
simply,
by cost
Yes,
carrier
yeah.
it's clear. Yeah. What about SSB?
Ma'am, actually, then it should pass through band pass filter so that only one side of like upper either lower will get passed.
Okay,
So,
and what band pass filter we pass through?
so it should have frequency in the range of like suppose we want to pass low pass filter, then the cutoff frequency should be like in the range of minus FC to minus FC plus FM. Union of FC minus FM. Kind of some things are there, ma'am. Not
Okay, okay, nice, nice. So yeah, whenever we require a modulation process, we don't pass it through a low pass filter. Just remember, we pass it to a band pass filter. In demodulation, we pass it through a low pass filter. So here itself, we will pass through a band pass filter. We will have DSB. We'll pass it to a band pass filter, and we will get SSB. And you should remember this AM modulation sorry term, AC 1 plus KAMT cos 2 pi FCT, and DSBSC, why we call SC, because it is a suppressed carrier. Yeah, question.
Ma'am, in generation of SSB through this frequency discrimination techniques are actually told about using LPF, ideal LPF and HPF for generation of this with its cutoff frequency at that
Okay,
carrier
okay, okay,
frequency.
okay, okay. Yeah, but yes, yes, okay. So generally, in the generation of modulation, this is a modulated signal, and this is a modulated signal. In that we require this one band pass filter, but sometimes in modulation itself, you require particular portion. So in that you can use low pass filter. So I my statement about
Yes,
DSB
ma'am.
is
Actually, sir was using this on DSB signal only. After DSB signal was generated, sir was using HPF, LPF to get SSB.
okay, HPF. So it is like Kirtis was saying, HPF, LPF. Nice, nice. So it's good that you all are remembering. So yeah. So you require, and just a multiplication of MT cos 2 pi FCT. So you have the spectra, this one. Yeah, one more thing. Where we use AM, where we use DSB, and where we use SSB in practical scenario.
Don't know, ma'am.
So SSB is used for modulation of voice signal. SSB used for modulation of voice signal. And one more term is there, VSB, vestigial sideband. So it is also used for modulation of a voice signal. And AM, since the AM modulation is having also carrier, but the AM modulation have the frequency of 553 kilohertz, 1105 kilohertz. Yeah, this one. So this one is the frequency range. So it is a kilohertz frequency, and we require it for the broadcast of some information through antenna. Like you remember Modi. Sorry, I want spelling name. So uh, uh, our prime minister has broadcasted one information during this national 15th August. So he was broadcasting the information through AM. So whenever that type of broadcasting is there, then AM is used. And whenever you require a specific equals to proportion of AM, then we use DSB, and SSB is used for voice signal, voice modulation. And FM sir has not taught yet, but yeah, FM you all know. We have FM radio, so 88 megahertz, 88.0 megahertz. So it has a megahertz signal. Okay. So yeah, this is the
Excuse me, ma'am.
yeah, yeah.
Ma'am, where this DSB-SC is used? DSB-SC signal?
Yeah,
Separate.
DSB-SC signal is not for specific use, but whenever we don't require AM, then we can use DSB-SC. But yeah,
Okay, ma'am.
DSB-SC is just a part of AM, right? It's a AM modulation itself. But here we have suppressed carrier. The carrier is not required. So whenever we have a very limited bandwidth, we don't require carrier, then we use DSB-SC. So it depends on the available spectra that we have in for a particular use case. So yeah, I'll move ahead to the question.
Excuse me, ma'am.
Yeah, yeah.
Ma'am, actually, what I heard like in video, like TV signals, so we need to send picture images as well as audio. So, as AM has a noise, a lesser noise immunity, we normally prefer AM kind of modulation for transmitting images. And whereas whenever we are dealing with the sound signals, we should use FM. So, SSB, is it useful for voice signals like application domain?
Yes, SSB is why SSB is used for voice signal, because the voice signal has a spectra of what is the voice signal frequency? Just let me know.
Uh, Voice, if it is a speech line, like then it will have only up to 0 to 3.7 kilohertz.
Yes, yes, 0 to 3.7 kilohertz, up to 0 to 7 kilohertz. So
Yeah,
it will have the spectra of this one, this type.
yeah,
And in base, after passing to a modulation process, this is a message signal. So since FC is far greater than FM, so we'll have something this type of spectra after modulation.
yeah,
So why this is why SSB is used, and sometimes we require VSB also. VSB because VSB has a smooth boundary, vestigial sideband. Have you heard about VSB?
yes, ma'am.
So these tools are used there. But yeah, you are very correct that the AM modulation is used for broadcasting of videos. So AM is used for videos. So I was not remembering proper broadcasting of RPM. So yeah, there we use the AM. For the FM broadcasting, we use the FM modulation, because there the noise is come here. The noise is directly proportional to amplitude. So here we use for the broadcasting of videos.
Ma'am, so AM has high noise immunity, right?
No,
No,
no.
no,
AM has lesser.
less. Why
Okay,
AM has lesser?
okay.
Because in you have heard about this one, AWGN,
Or
additive white
additive white
Gaussian.
Gaussian line.
Yes, yes.
Yes,
So
yes,
this
ma'am.
additive white Gaussian noise is adding to the amplitude, and here in the AM signal we are varying the amplitude. So along with the
Okay, ma'am. Okay.
modulation, the noise will also increase. But in frequency modulation, we are varying the frequency, so the noise will not be there. So the noise immunity for AM is less than the noise immunity for FM. So Kirti was very correct. Here we use for the video signal. And frequency also matters. Like for the video signal, we have a frequency of 0 to 4 megahertz. So we have to make sure this frequency matches with this or not. I'll confirm it tomorrow, next session. Like where we use, like I remember it is used for video broadcasting or image broadcasting. So this frequency matches or not, I have to check it. So okay. So let us move to the questions. I think 1 hour left. So do you have any doubts in the theory part? Because it was very easy this time. This AM modulation is about to end in one or two uh, lectures. Like in the next lecture, so you will have VSB, vestigial sideband, and then AM modulation ends there. Then you will have frequency modulations and then receivers, super heterodyne receivers and all. So yeah, so that receiver part is very important. So let's move to the questions. I think everybody has watched this lecture. I want I want you to introduce the sampling theorem and yeah, just yeah, Hilbert transform. This is one of the very hot topic today. Why we use Hilbert transform. So what is the Hilbert transform? This one, after this one we'll solve the questions. Kushal,
Yes,
you are
ma'am.
asking about Hilbert transform. Yeah.
Yes, ma'am. So what I have to say, ma'am, here? What is its
Hilbert
frequency
transform
spectrum?
and where it is used and what is the basic convention of that?
Okay, ma'am. First, ma'am, I will tell about its use. First one is to generate SSB, sir told us about, and second one is to get that complex envelope, pre-envelope, something like that, of the passband message signal.
And what is Hilbert transform?
Ma'am, its frequency domain spectra is like it shifts. It has no effect on magnitude, but it shifts the positive frequency by -90, negative frequency by +90.
Ma'am, what I feel is Hilbert transform is a tool with which we can shift a signal by 90 degrees. For that purpose, we can use it.
Yes, yes, yes. Yeah, yes, yes. So Hilbert transform is a LTI system, first of all. In LTI system, suppose you have A cos omega t, then the output will be A dash cos omega t plus phi. Okay. So whenever a sinusoidal signal is passed to a LTI system, then we will have the same sinusoidal signal with a different amplitude and different phase. So that's why we everywhere we use sinusoidal signal for the analysis of any system. So yeah, so if we want the analysis of this LTI system, this one is. And Hilbert transform, as Kirti said, and Kushit, you were also right, like it is where it is used. So it is A cos omega t and A dash. We are not talking about the phase, the amplitude here. Cos omega t plus pi by 2. So it is giving a phase shift. And in time domain, it is represented as ht is equals to 1 upon pi t. Okay. And so, yes, I want you people to calculate the Fourier transform of Hilbert transform. ht is equals to 1 upon pi t. What is the Fourier transform of this? It's minus j.
Ma'am, we have to calculate it actually.
You have calculated. Do you want to tell me how you will you calculate? Like, Kushal, I told you to calculate the Fourier transform of mod of x, mod of t. You have calculated the
Okay.
growth in terms of omega square, right? Then you can how you can get 1 upon omega square with omega with differentiation, right?
Yes, ma'am.
So 1 upon omega you will get somewhat this type of term. So you have to use the properties of Fourier transform. I want you to calculate. I can calculate actually, but I want you to calculate.
Okay, ma'am.
Yeah, yeah.
I'm trying.
Yeah, take your time. Kirti, you please also try.
Yes, ma'am.
Akhila, are you here? Yeah, please
Yes,
calculate.
ma'am, I'm here, ma'am.
You please calculate. You will have much more understanding.
Yes, ma'am, I got it.
Yeah, what's the answer?
1 upon pi t. It's minus j times signum f.
Nice. So you have calculated this part now. I will answer you in this part.
Okay.
So how you have calculated?
I took signum function. When I differentiate it, I get 2 times impulse, 2 times delta t. We know that differentiation property of Fourier transform,
So
that if
you
x t.
have calculated
Yes,
you
ma'am.
predicted first that you know the Fourier transform using signum and then try to calculate, right?
Yes, ma'am. Yes, ma'am.
Okay. I want this first bit. Okay, no issue. You have calculated. Akhila, you're trying?
Yes, ma'am.
Yes. So answer is this one, which is correct. So okay, I'll solve. Kushal, you have calculated this mod of T Fourier transform, right? What was the answer?
Then minus 2 by omega square.
Okay. Minus, right? Using the duality. And how will you get minus 1 by 2 t square to t, t power minus 2? So if you differentiate it, minus 2 to n, so you will integrate, you have to integrate. How will you get 1 by t square to 1 by t? Differentiation and integration will not work here. 1 by t square to 1 by t. I'm calculating using this one only. Mm, okay. So sometimes we don't have hope how to go from this. You can try with this also. ht is equals to 1 by pi t. So hf is equals to minus infinity to infinity ht e power minus j 2 pi ft dt, minus infinity to infinity 1 by pi t e power minus j 2 pi ft dt. So 1 by pi minus infinity to infinity t power minus 1 minus j 2 pi ft dt. So you know that this term will not have an easy integration. So we know that this one is minus infinity to infinity x power n minus 1 uh, what is the gamma? What is the formulation for gamma function? E power minus x, I think, dx. Yes, yes, yes. So yeah, this is a gamma n, and gamma n plus 1 is equals to n gamma n and factorial n. This is the formulation. So here, xf you can calculate using this one, and you have to formulate this one using a gamma function. Has anybody heard about gamma function earlier? You people might have heard about.
Yes, yes, ma'am. Not very deeply about this function, but we know that this
So
n
here
gamma n
basically
and
you can
gamma
use
of
this
half.
form of this, and you'll
Yes,
get
ma'am.
the formulation of the signum f. So now this is the first way, and the second way which you have solved, which is the easier one also. I think you have just taken signum f, right? Which is 1 for f greater than 0, minus 1 for f less than 0. So signum f, right? So how the j signum f comes? So yeah, so I'll solve in my way. Consider a function e power 1 upon alpha plus j omega minus 1 upon alpha minus j omega. So e power alpha t and e power minus alpha t. So t greater than 0, t less than 0. Why I'm taking this alpha or anything you can take. Consider this function f of t alpha. So yeah, consider this function. Why I'm taking this one? Because I know signum function how it looks like. The signum function looks like 1 minus 1 for t greater than 0 and t less than 0. So I'll just tends to alpha to 0, then it will be same. So and then try to find the Fourier transform of this one. So f alpha f is this one, or omega you can say this one, because for t greater than 0 it is 1 upon alpha j omega, and for t less than 0 alpha minus j omega. And solving it, f alpha omega 1 upon alpha square omega square minus omega square, and j square will be plus. So alpha minus j omega minus alpha minus j omega. So it will be what it will be, minus 2 j omega divided by alpha square plus omega square. And when alpha tends to 0, then f alpha omega is equals to minus 2 by j omega by omega square. It is minus 2 j by omega, and you can write minus 2 by, sorry, here if you write j, so j omega, 2 by j omega. And if you tends alpha to 0, f alpha t is equals to alpha tends to 0, then 1 t tends greater than 0 minus 1 t less than 0. And here it turns to Fourier transform of 2 by j omega, and is nothing but a signum t. Using duality, you will have 2 by jt as signum f. Here minus, because minus should be there using duality. So you will have 1 upon jt as minus j signum f. And if you use pi also, pi terms, where the pi terms comes, yeah, to see it is a 1 upon j 1 upon 2 upon j 2 upon T is having this one. Um, Question you have also solved now. Can you please check with the answer?
Yes, sorry, ma'am.
Yeah. Can you check with the answer? So yeah, here 2 by j omega it is there. So yeah, he was wrong.
Yes,
In the last term I have done the mistake. So here t, so you have 2 pi t, right? Because omega is equals to 2 pi f, right? So in terms of f,
yes,
I'm
ma'am.
writing t. So it should be there. And 1 upon pi t will have minus j omega. So yeah, this is the answer. In the
Yes, ma'am.
first way, you just have to using gamma function. In the second way, I'm trying to solve using answer part using signum function. So it is nothing but like this. I'm trying to consider this function where at the end I'm limiting alpha as 0, then so that I'll get the signum function when alpha tends to 0, and then I'm trying to calculate the Fourier transform of this function. This function is having this function, and then using duality we are able to get this. You please remember this formula because we don't have much time to solve every time this formulation. I hope you got clear. And how to solve here like this?
Yes, ma'am.
You have to consider n minus 1 is equals to minus 1, and x is equals to minus j 2 pi f t. So remember t is this much. So you have to formulate it. I want you to calculate using the gamma function, a one step formulation. So yeah, Hilbert transform is done, I think. So let's move to the questions. What is that? So vestigial sideman has sir has taught in the module 4, I think. Sir has taught.
No, ma'am.
Okay, sir has not taught. Okay, no issue. So I think it's in module 4, lecture 21. Okay, I think it's not there. Sir has calculated Hilbert transform, Fourier transform. Sir, how sir has calculated? So you can also refer to the sir, how sir has calculated. Actually, I don't remember anything. So I try to calculate it and try to prove it using a right hand side. So you can also calculate using left hand side, no issue. But please do check how sir has calculated. So yeah, so I told you
Ma'am,
this is the
I did like that only. How sir taught us.
okay, okay. How sir has calculated?
Ma'am, by taking this other way around, first signum t, then we
Okay,
know that derivation of signum
the
t has.
second way I have calculated, right? So, but yeah, I have taken alpha
Yes, ma'am.
term. So I tried to formulate using a sigma function how it looks like. So yeah, one more thing, you have minus j signum f, right? As a Fourier transform of 1 upon pi t. So how it looks like? So I try to focus on this. It looks like, how it looks like? It is a minus j, it's it's a minus j for positive and plus j for negative, right? And j, how you can write? E power j pi by 2. Why? Cos pi by 2 plus j sine pi by 2. We know that it is 0. So here we can write, and sine pi by 2 is equals to j. So it is 1. And similarly, you can write minus j as is equals to e power minus j pi by 2. Why I'm writing in the term of this pi by 2? Because this plus j is representing a phase shift by positive pi by 2. A minus j is representing a phase shift by a negative pi by 2. So I'm writing like this. Minus j into 1 is equals to j and equals to j. So please remember this. It's j means a phase shift by pi by 2, and minus j by means minus pi by 2 phase shift. So why signum f is important, and signum f it is doing actually a phase shift of minus pi by 2 to all the positive frequencies, and plus pi by 2 to all the positive frequency, and it is actually giving a quadrature phase shift. So yeah, question.
Ma'am, what is the physical significance of this negative frequency?
Yes.
Does it
So,
has any
ha.
physical?
So in actually the spectra, we in bandwidth calculation, the bandwidth is defined as the only positive frequency, right? It is defined as only positive frequency. But in a spectra, what we are getting a mirror of in the negative frequency. So we are actually getting the modulation in as a mirror of the negative frequencies. So it is showing that you have a mirror like spectra. So here if you have positive frequency, the similar thing you will get in the negative frequency. So that's why we consider negative frequency. But yeah, physical significance is nothing, but we are just trying to we are using negative frequency to represent a mirror of the AM modulation, FM modulation and all. But yeah, we don't use the negative frequency in bandwidth calculation in practice.
Okay, ma'am. Suppose one cost function is passing through this Hilbert transformer. Then simply we will add the phase shift of minus pi by 2 in the expression, right?
No, we also add the sorry, pi by 2 to the negative frequency, because in practice we don't consider negative frequency, but yeah, we for the mathematic formulation you have to write.
Yes, ma'am.
Yes.
In mathematically, suppose ma'am, I have given this expression cos 2 pi ft. Then simply after passing through, we will write cos 2 pi fct minus pi by 2, right?
Yes, yes.
Okay, ma'am.
Yeah, in my case, what I taught earlier, LTI system. So plus in the you will have the suppose input as sinusoidal signal, then output as also as a sinusoidal signal with some phase shift, and that phase shift is pi by 2. Positive, negative depends on the frequency of the nature of the frequency. So yeah, moving to the questions. Yeah, questions is there in other the. Sorry, I got late in dealing with the questions, but yeah. So let us solve these questions. I think you all remember these questions. Yeah. Which of the
Yes, ma'am.
following
C.
gives at a highest bandwidth efficiency?
SSB.
Adila. SSB. Yes. So answer is SSB. Why it is SSB?
Ma'am, it sends the same information within minimum bandwidth possible. So,
Why efficient? What is efficiency? So efficiency is only the message signal. If like I'm transmitting the information, I'm transmitting the voice message to you guys, but the actual message and it is transmitted by some means, which is a carrier. Which is, but carrier is actually helping me to transmit my information to you, but a carrier is useless, right? So the only required is message. So message is required, and it is containing the actual information. It was a baseband which was not able to transmit, so we are trying to transmit using carrier. So in DSBSC, you know that you will have a waste of information also. As I told you, this particular message is actually the same one, but actual content information can be passed through a single sideband as well. So the efficiency is calculated using this, and so SSB has a proper only message, no carrier and no USTL information. And since it is a smaller in size, so it will be able to efficiently it can transmit through a path. So we can have this as a more efficiency. Efficiency. I'll try to deal with one formulation also. What is the formulation of this one? Formula of this? Mu squared over 2 plus mu square, right?
2 plus mu square.
Yeah, this is the actual last formula. What is the initial formula? What was the initial formula?
I don't remember the numerator, but denominator is total power of AM.
Yeah, total power of AM.
numerator is that message content
Message content
power.
power. Yeah. when you have total power more and this message power as the more, so you will have better efficiency, and maximum efficiency we can achieve is 50% only, because mu can be sorry 33%, sorry 33% for AM. For DSB SC I think it is 50%. Why? You have to look at the mu. If mu maximum, it can be 1, so it 1 by 3 and it is 33%. So you have to remember like this. So modulation technique in the signal xt is equals to AC1 plus KMT cos 2 pi f ct is
Ordinary amplitude.
Ordinary amplitude modulation, ma'am.
you also remember please vestigial sideband. I think sir will taught in the next class. Sir will teach in the next class. So it is here. The frequency response of the Hilder transformer is, transformer should be there, or transformer we can write. It's LTIC.
First one.
Or minus
All
is
this.
sigma of S.
Okay. If somebody has some problem, please look at that. Yeah, I want you to solve this question. Consider the signal xt is equals to AC cos 2 pi of ct plus k sin 2 pi fmt. Pass through a square law device with output yt is equals to input xt. I'll write yt is equals to xt square, and then output is passed through a band pass filter with a center frequency of fc. What is the DSBSC signal generated? Please solve this, please.
Ma'am, I think its answer is two. Second, B option.
Okay, answer is the B option according to you. Okay. Yeah, I want all of you to answer.
Yes, ma'am. Yes, ma'am.
Option B, ma'am.
Option B.
Something.
Okay, all
Yeah,
of you are
ma'am.
correct. Congratulations. So option is
Yes,
B.
ma'am.
Why option is B only? Because to ACK here you want FM. You remember you want FM, but it will be actually to it will make to a band pass using FC cos 2 pi FCT. Here it won't pass. Here it won't pass. So only answer is B. This term is passed. YT is equals to 2ACK sine 2 pi FCT cos 2 pi FCT. Yeah. The power of the DSB-AC signal to cos 2 pi FT cos to 2000 pi T is,
Ma'am, one.
what is? Answer is 1. Okay, let others
Yes.
know. Answer, according to question, answer is D.
Ma'am, how to solve it? Actually, I did it wrong in the assignment.
Okay. So you know how to calculate the power of a DSB-AC signal? It's the power of DSB SC is 1 by 2 AC square into power of message signal. First of all, how DSB-SC signal looks. So it looks like AC MT cos 2 pi FCT. You just remember MT into carrier. Okay, so how will you calculate this power? The power of the this cos or sine. It's simply but a amplitude square divided by 2. And what is the power of message signal? It should be power of message signal, right? So it is, if we have amplitude of AC, then AC square by 2 into PM, power of message signal. Here you have question as, what is question? 2 cos 2 pi t. Question is 2 cos 2 pi 2 pi t into cos 2000 pi t. So here what is empty and sorry, carrier? You know that FC is far greater than FM. So here it is FC.
Cos 2.
It is FC. So how it will look like? AC square by 2 into PM. So 1 by 2 into AC square is 4 and 1 by 2. You know now how to calculate the power of a cosine signal. It is only a magnitude square divided by 2. So it is 1 by 4 into 4. Yeah, Kurshid is very correct. Answer is 1. So you just remember this one. Uh, have you got?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay. Consider a message signal with spectrum limited to FM and carrier frequency FC. The corresponding single sideband modulated frequency signal with upper sideband occupy the spectra. From your understanding, like you were telling about LPF, UPF, HPF. What was that?
B option is there.
Yes, ma'am. B.
Okay. So why it is B? Because it is a upper sideband, right?
US upper sideband.
So answer is B. Okay, nice. You please also remember how it is coming. Don't just remember, okay? Okay. Moving to the next question. Uh, Given the message signal MT and the carrier frequency FC, the modulation AXT is equals to AC MT cos to S termed as. It's very easy.
Yes, BSc.
Yes, previously, ma'am.
Okay. So these type of questions also asked in your assignment. And I'll tell you from my experience of your exam. So I want to know, all of you are giving exam for this course?
Yes, ma'am.
Yes, ma'am.
Akhila, you?
Ma'am?
Are you giving exam for this course?
Yes, ma'am.
I cannot hear you.
Yeah, ma'am.
Okay, you're giving. Okay, nice, nice. So
Yes, ma'am.
in almost 30% of the questions are directly like this. So you can easily gain, and don't worry about the certificate. You'll definitely get, because you are solving the assignments properly, and you just remember how it's coming. So you'll get. So nice. Nice to know that you are planning for the certificate. Yeah, Kirti.
Excuse me.
Hmm.
Ma'am, that exam will be like a multiple choice question type,
Yes,
either
yes, yes.
descriptive.
Totally multiple choice question.
Okay.
And yeah, I have given exam of one subject, so it was completely multiple choice question. And you can also try for gold certificate if you are able to solve all the questions. So just remember how it is coming. So yeah, moving to the next question. The output voltage V2T of a nonlinear device can be expressed in terms of the input voltage V1T. Hey, this was a direct question asked in the gate exam. Gate question. So how many of you are planning for gate also? Kushid, are you trying for gate?
Yes, ma'am. Actually, I gave GATE examination this year. I'm waiting for result.
Yeah, yeah, please. You gave already. Okay, nice. How it went?
Ma'am, it was actually difficult, but I did my best. Let us see what rank I'm getting.
Okay, you can also try this time. So yeah, so if you are learning from the NPTEL, then you can definitely try for the GATE exam, and it will be very easy for you to have understanding and all. So Akhila, you are a BTech student. Are you planning for GATE?
Yeah, ma'am. I'm planning
Yeah,
for
yeah, yeah. Sure, sure.
for
You
that.
should plan. So yeah, it was a great question. Please solve this question. I will also solve. So let us solve. Since it is a bit difficult question, I'll solve for you. Question number 8, solution. Since it is a given square law,
Ma'am, 2 times A2 by A1.
2 a2 by a1 answer you are saying. What is the option? Option is
Yes,
D.
ma'am. Option D. Option D.
So, wow, question you have done very correct. So, answer is D. So, you are able to solve this question. Nice, nice. Kirti and Akhila, you please also try.
Madam, I tried and the answer is B, but the last page, like how the divide by A1 comes,
Okay, okay,
is,
I'll solve for you. No
um,
issue. Akhila, are you able to solve?
Actually, I don't know how to solve this question, ma'am.
Okay, I'm not able to hear you properly. So, okay, let's solve this question. So, Kushit has already solved. Nice. So, V2T is equals to A1V1T plus A2V1 square T. So, it is given for you, this expression. And input signal V1T is equals to AC cos 2 pi FCT plus MT. So, how we will calculate V2T? Just put in the expression. So A1 AC cos 2 pi FCT plus MT plus A2. Just let me know if I did any mistake. AC cos 2 pi FCT plus MT square, which is A1 AC cos 2 pi FCT plus MT plus A2. Yeah, same. I'm writing same again. Not required. So just write A1 AC 1 plus 2 A2 by A1 MT cos 2 pi FCT plus A1 MT plus A2 MT square T plus A2 AC square cos square 2 pi FCT. We know that this term is at carrier frequency at carrier. So I'll write different color. At carrier frequency Fc, and it is a desired AM signal, right? And the remaining terms we have to remove it by the filter because we require modulation term, right? So what should be the K? It should be this one. I hope you got it. This will be
yes, ma'am.
filtered by filter.
Ma'am, actually, I have one more doubt which is related with the basic equation of AM.
Yes, yes, true. Ask.
Ma'am, actually, most of the times every time actually we are writing like amplitude modulated signal. So it is equals to AC in the AC into the bracket 1 plus KMT multiplied by carrier. So that K signifies, as per me, actually it is sensitivity factors. That way we have discussed on very first lecture, right?
Mm-hmm.
And sometimes we are using it as a modulation index.
Yes, yes, yes. So yeah, this is the amplitude sensitivity. Very nice question. I also used to had this doubt.
Actually, you asked me very first time you asked me what is unit of this K. So I said unitless. So I was thinking like it is a modulation index. So ratio of two voltages. So it should be a unitless.
No, no,
So
no. It will will be 1 by V or 1 by I. So you in the questions you might deal with this. So Ka should have the unit, but because it is a numerical, and here it should have numericals. The unitless quantity should plus to the unitless quantity, right? This one.
Hmm.
And empty will
Hmm.
have some unit. So here Ka will have unit. It depends on the unit of empty. So yeah, the heat K is always defined as the amplitude sensitivity. Yeah, but the modulation index is defined as Ka into mod of empty, amplitude of empty, or sometimes it is written as Am by Ac, because in modulation of this A, you will have this one Am modulation, right?
Yes.
So why I'm writing like this? Am. Here what is the term? AC1 plus, what is that term?
Mm,
1 plus k into empty.
Yeah, it is multiplied by AC1 plus KAMT. Here AC1 minus KAMT. So this magnitude, it is a AM max. It is AM max, and it is AM min. So what we are doing it, the maximum proportion of the amplitude, which is what we are doing as modulation in AM modulation, with respect to minimum proportion of the amplitude, what is that ratio? It is represented as modulation index. But yeah, mu is never equals to Ka. Mu is equals to Ka into maximum of magnitude of MT. So this one, because here in this AM max, if you see, what you are doing is AC1 plus KAMT. So you are varying this AC plus, so you are varying this AC KAMT. Here MT is a magnitude of AM. Just remember this. You are varying AC by some factor of this one. So this factor is modulation index. And where it is AM by AC, you have to check for the specific case, but it is not always equals to AM by AC. But yeah, it is always equals to this one, always. And I told you mu is unitless quantity. Why mu is unitless quantity? Because here, suppose MT will have magnitude of mu is Ka into MT magnitude. Suppose it will have 1 by V into V, so it will have no unit. So that's why mu has no unit, but K has unit. I hope this clears.
yes, ma'am.
Yeah, so you're just remembering it is the proportion by how the modulation occurs. Moving to the next question. This is the second last question. So yeah, consider the message signal MT is equals to cos 2 pi 200 pi t. Let the carrier frequency FC is equals to 110 k kilohertz, and the carrier amplitude AC is equals to 10. With 75% modulation, what is the efficiency of the AM signals? So you have to remember what is the efficiency formula for the AM signal.
Yes, ma'am. D.
Answer is D.
Okay, nice. Akila, are you able to solve?
Yeah, I have solved the assignment.
You have
I
solved in the
I
assignment.
get answer as 21.95%.
So how you have calculated? Tell me the formula, Akila.
1 minute.
PM is the power of message signal. So I don't need to calculate, I think. K, K is given as 7. Here 9 by 16 to 1 by 2 divided by 1 plus 9 by 16 to 1 by 2. So answer you have calculated as 2 1 plus 9 5% is. So last question. Consider the message signal sine 150 pi t. The SSB modulated signal with LSB corresponding to the carrier frequency FC is equal to 2100 hertz is. You have to use the formulation of Hilbert transform also here. Kirti left, I think. Kurshid, are you solving?
Ma'am, answer will be yes, ma'am. Answer will be D.
So how you are solving?
D. Ma'am, I didn't write that Hilbert transform, but here it is saying that lower sideband will be present. So FC minus FM will be present, and I calculate FC minus FM. Here it is 75 hertz message signal and carrier signal 2000 hertz. So FC minus FM comes out to be 1925 hertz, and multiplied by 2 pi we get 3850 pi, which is only present in D option.
Okay, okay. So this is a nice way to calculate. Like he's telling this FC minus FM frequency. He's not using Hilbert transform, and FM is equals to 75 hertz. Yes, 75. Yeah. So how you are calculating FC is equals to 2000 hertz? You are calculating using your options, right? You are checking whether any one satisfy or not.
Yes, ma'am.
Hmm. So FC minus
Yes,
FM you
ma'am.
calculated.
And
Yeah.
actually, I ruled out that first one. First one corresponds to DSBSC type of modulation. So I had to check only from these three options.
Yeah, yeah. This is a nicer way how we can solve this question. So yeah, nice. Other method is using Hilbert transform. You can solve. So I think I should leave. 7:50 have some other meeting as well. So yeah, if you have any doubt, you can just mail me in this mail ID. This is the IITH mail ID. So just mail me. And what are the homeworks for you? It was a homework for the sampling theorem, flat top and the pulse sampling. And the second one is using gamma function. Why I'm asking you
Band
to
pass.
use the
Ma'am, band
gamma
pass
band pass
sampling.
sampling? Nice, nice. Other one, why I'm trying to use, trying to know about the gamma function, because it is very helpful to solve in your mathematics as well. So just go through that and let me know if you have any doubt. So I would like to conclude the session.
Okay.
Thank you all for joining. Okay.
Thank you, ma'am.
Okay. Okay.